So I want you to try a little thought experiment with me right now. Wherever you happen to be listening to this, just, look around your immediate environment.
Yeah, just pick an object.
Right, exactly. Like maybe you're sitting in your living room and you're looking at a painted wall. Or maybe you're on a train staring out the glass window. Or, just look down at the device you're using to listen to this and then look at your own hand holding it.
The physical world.
Yeah, the physical world, it presents itself to us as incredibly solid, incredibly continuous and permanent. But what is it all actually made of? And I don't mean the cells in your skin or the microchips in your phone.
You're talking about going deeper.
Much deeper. I mean, if you zoom in past the biology, past the microscopic fibers, down to the absolute basement of physical reality, what is the fundamental stuff building our universe?
The building blocks.
Right. And the answer, as you probably know, is atoms. But knowing the word atom and actually understanding the frankly mind-bending reality of what an atom actually is, well, those are two completely different things.
Oh, absolutely. I mean, it really is the ultimate magic trick of the universe. We experience this grand illusion of solidity, right?
Yeah.
But it's entirely generated by a hidden, turbulent, microscopic world that we can't even see.
Which is just wild to think about.
It is. And the journey to uncover that hidden world, to kind of pierce through that illusion, it's easily one of the most astonishing achievements of human intellect. We didn't just find the atom. We had to basically invent entirely new ways of thinking just to comprehend it.
And that is exactly our mission for this deep dive. Today, we are tracing an epic 2,000-year detective story.
It's a long one.
It really is. We're going to explore how humanity transitioned from, honestly, literally just guessing what matter was, to actually cracking open the fundamental building blocks of reality.
Step by step.
Exactly. We have a really fantastic stack of educational source material today, covering the history, the physics, and the chemistry of the atomic model. And our goal is to treat this like the most fascinating, engaging science seminar you've ever attended.
No boring lectures here.
No, definitely not. We are going to break down this incredibly complex subatomic world, and I promise you, we are not going to gloss over the tough stuff. We aren't going to just give you a dry list of dead scientists and dates.
Right, because that misses the whole point.
Right. We are going to explain how these discoveries were made and why they force us to question the very nature of existence itself.
Which is crucial, I think, because the history of the atom it's really a story of relentless, almost obsessive human curiosity. It's a story of incredibly elegant models being built by one generation, celebrated as absolute truth, and then
completely shattered by the next generation.
exactly, completely shattered by the experimental data of the next generation.
Yeah.
It's science functioning exactly as it should, by proving itself wrong in order to get closer to the truth.
I really love that framing. But to start, I actually have a genuine logistical question. Because today, if we want to look at a subatomic particle, we build, billion-dollar subterranean particle colliders, like the Large Hadron Collider in Switzerland.
Right, massive machines.
Yeah, or we have these electron microscopes that cost more than a small island. But how did anyone even conceptualize the idea of an atom before any of that technology even existed? I mean, where does the concept even begin?
Well, to find the very first whisper of the atom, we have to rewind the clock way, way back, over 2 millennia.
Wow.
Yeah, we have to leave the modern laboratory behind entirely and step into the realm of pure philosophical deduction. So we're heading back to the ancient intellectual landscapes of India,
Okay.
specifically around the 6th century BCE, though, some scholars argue it could be even earlier than that.
Right. The source material actually introduces us to this fascinating ancient Indian philosopher named Acharya Kanada. And he was essentially trying to solve this giant puzzle of what constitutes the material universe. And he developed a framework that was recorded in these ancient Sanskrit texts known as the Vaisesika Sutras. And Kanada proposed that if you take any physical matter, which he termed dravya, right?
Yeah, dravya.
If you take this dravya and you begin to divide it, you can't just keep dividing it infinitely forever.
Exactly. He argued that there has to be a physical limit to reality.
And I have to pause here because looking at his reasoning is just remarkably sophisticated for the time.
Oh, it's brilliant.
Because a lot of ancient thinkers, they believed matter was continuous, like a perfectly smooth fluid that you could theoretically just keep cutting in half forever.
Right. Aristotle thought that too.
Yeah. But Canada realized there's a logical paradox there.
Yeah.
Let's say you have a grain of sand and you divide it infinitely, and then you have a massive mountain and you divide that infinitely.
Okay, I see where you're going.
Well, then both the sand and the mountain are composed of an infinite number of parts. And mathematically, if they both have infinite parts, how can one be vastly larger than the other?
That's a great point.
Right. To avoid that paradox, he deduced that division must eventually stop. Like, you must hit a fundamental unit that literally cannot be broken down any further.
And he had a name for it.
Yeah, he called this ultimate uncuttable particle the Parmanu.
The Parmanu. It's just a brilliant piece of deductive reasoning. And Canada didn't just stop at proposing a single isolated speck of matter either.
Oh, he went further.
Oh, yeah. He theorized that these Parmanus must possess an inherent urge to combine, like they don't just sit there alone. He suggested they form pairs, which he called dyads, and then groups of three, or triads.
Okay, so they're building blocks.
Exactly. And through these endless combinations and, like, geometric arrangements, the entire visible universe is constructed, from the wind and the earth all the way up to human consciousness itself.
Which is just wild because right around the exact same historical period, thousands of miles away, the Greek philosophers Leucippus and his student Democritus, they were basically executing the exact same mental gymnastics.
They were.
Like, they were standing on the shores of the Aegean Sea, looking at how water eroded rocks and deducing that the rock must be made of tiny, invisible grains.
The same exact logical leap.
Yeah. They arrived at a strikingly similar conclusion to Canada, and they coined a term that we literally still use right now, atomos.
Atomos.
And in ancient Greek, atomos literally translates to uncuttable or indivisible.
It's so important to recognize what a massive cultural and really psychological pivot this represented for humanity.
How so?
Well, think about it. Before thinkers like Canada and Democritus, explanations for natural phenomena were almost exclusively mythological or theological.
Oh, right, like the gods were angry.
Exactly. If a plague swept through a city, it was divine retribution. If a volcano erupted, well, the gods were at war. By proposing the Parmanu or the atomos, these philosophers were shifting human consciousness away from magical explanations and towards structural, mechanical ones.
That's a huge leap.
It is. They were boldly claiming that the universe operates on physical, invariant rules, regardless of what the gods might be feeling that day.
I see the philosophical beauty in it, I really do, but I do have to play devil's advocate here for a second.
Go for it.
As brilliant as Democritus and Canada were, this was entirely a thought experiment.
Sure.
I mean, they didn't have chemical regents, they didn't have vacuums or high-voltage electricity. They literally just sat around, looked at nature, and thought incredibly hard until they logically deduced the atom.
Yes.
And because they couldn't actually test it, wasn't it basically a scientific dead end?
Well, you've hit on the exact limitation that basically stalled human progress on this front for nearly 2,000 years.
2,000 years.
Yeah. It was brilliant philosophy, but it lacked the crucial mechanism of science, which is empirical verification. Because they had absolutely no way to run controlled experiments, they couldn't determine, like, the mass of these particles or the rules by which they bonded.
Or why a rock is different from water.
Exactly. Or why one type of matter behaved differently than another. And honestly, Aristotle actually rejected Democritus's atomic theory.
Oh, really?
Yeah, he favored the idea that everything was made of four continuous elements: earth, water, air, and fire.
Oh, the classic four elements.
Right. And because Aristotle was just so wildly influential, the concept of the atom was largely suppressed or just ignored for centuries. It became this piece of historical trivia rather than a working scientific model.
So we have this profound, game-changing idea of an indivisible building block, and it just sits on a dusty shelf in the library of human history.
Pretty much, yeah.
It takes literal millennia for our technology and our scientific method to finally catch up to ancient philosophy, which I guess brings us to the moment where the modern era of chemistry actually begins.
Right, so we're going to jump forward to the year 1808.
Okay, 1808.
We are in England, and we meet a polymath named John Dalton. And Dalton is the man who finally drags the atom out of the realm of abstract philosophy and forces it to stand up to the rigorous scrutiny of physical experiments.
And Dalton's background is actually really crucial to understanding how he figured this out, right? Because he wasn't originally looking for atoms.
No, he wasn't.
He was a meteorologist, he was obsessed with the weather, specifically how gases behave in the atmosphere.
Yes, Dalton was endlessly fascinated by the air we breathe. He
Mhm.
wanted to know how, for example, water vapor could absorb into the air without the air just expanding uncontrollably. So through a series of meticulous experiments where he was mixing different gases, he realized that air couldn't be a single, continuous, homogeneous fluid. It had to be a mechanical mixture of discrete, independent particles just bumping into each other.
And this leads him to what chemists call the law of multiple proportions, which is really the smoking gun for atomic theory.
It absolutely is.
Okay, let's unpack this without getting bogged down in like 19th century lab reports.
Rees.
So Dalton noticed that when elements combine to form compounds, they always do so in incredibly specific whole number ratios.
Yes, whole numbers.
Right. For example, if you combine carbon and oxygen, you can make carbon monoxide, which is, a deadly gas. Or if you add exactly twice as much oxygen, you make carbon dioxide, which is what we exhale.
Exactly.
But you never get like carbon 1.5 oxide.
No.
The math always results into these neat whole numbers.
And the mathematical reality is the crucial insight.
Yeah.
Because why would nature insist on whole numbers?
Right. Why not fractions?
Dalton realized there's really only one logical explanation. The chemical elements themselves must be composed of fundamental, indivisible units. You can have 1 unit of oxygen, or you can have 2 units of oxygen.
But you can't have half a unit.
You simply cannot physically have half a unit of oxygen.
It's almost like discovering that reality is digitized. Like, before Dalton, people thought matter was analog, like a smooth, continuous ramp. But Dalton proved that matter is actually quantized.
Like a staircase.
Yes, exactly like a staircase.
Yep.
You can stand on step 1 or you can stand on step 2, but you can't stand on step 1.5. You just fall through.
That is a highly accurate way to frame it. So based on these gas experiments, Dalton publishes his formal atomic theory in 1808.
And what does he officially claim?
He states unequivocally that all matter is composed of incredibly small, indivisible particles called atoms. He proposes that all atoms of a specific element, let's say gold, are completely identical in mass and properties, while atoms of different elements have different masses. And most importantly, he declares that atoms can never be created, destroyed, or split into smaller pieces during a chemical reaction.
They just shuffle around.
Exactly. They simply rearrange themselves.
He essentially gives us what we call the solid sphere model.
Right.
Like, if we think about how a computer screen is made of millions of tiny individual pixels that cannot be split, Dalton was saying the universe is made of 3D physical pixels.
That's a great analogy.
They are the solid, unbreakable foundation of reality, like a giant Lego set, and atoms are those little one-by-one bricks that you just can't snap apart.
And Dalton's theory was a monumental milestone, because it provided the very first scientific, measurable description of how matter is constructed.
It wasn't just philosophy anymore.
No, it finally gave researchers a framework to test. If atoms had specific weights, well, you could measure them, you could catalog them. It ignited an absolute explosion of chemical discovery throughout the entire 1800s.
But science is a ruthless process, isn't it? Dalton proves that matter is made of these solid, unbreakable spheres. But the moment you hand humanity a purportedly unbreakable sphere...
The very next question is, what happens if I try to break it?
Exactly. Let me get a hammer.
Yeah.
Because Dalton's model explained how chemicals combine, but it didn't really explain why they combined, right?
No, it didn't.
If everything is just a solid microscopic billiard ball, why is oxygen an invisible gas and iron a heavy magnetic metal?
Precisely. The solid sphere model was incredibly useful for early chemistry, but it was physically incomplete. It treated the atom as a black box you couldn't see inside.
Right.
But toward the end of the 19th century, physicists began playing with a new, terrifying, and completely invisible form of energy.
High voltage electricity.
High voltage electricity.
Which brings us to 1897. We enter the Cavendish Laboratory at Cambridge University, and we meet a physicist named J.J. Thomson.
Yes.
And this is the exact moment where Dalton's unbreakable solid sphere gets violently smashed into pieces.
It really does. Thomson was investigating something that had been puzzling physicists for decades. It's called the cathode ray tube.
Okay.
And to understand how revolutionary his discovery was, we need to understand this device. So imagine a glass tube, completely sealed.
Got it.
Thomson used a vacuum pump to suck almost all the ambient air out of it, creating this very low-pressure environment inside. Then, at each end of the tube, he placed a piece of metal, an electrode.
Okay, one at each end.
Right. And then he hooked those electrodes up to a massive battery, applying a huge electrical voltage across the empty space inside the tube.
So he's essentially artificially engineering a lightning storm inside a vacuum tube.
That is a perfect visualization. When he cranked up the voltage, the glass tube would suddenly glow with this eerie kind of phosphorescent light.
Oh, wow.
Yeah, a mysterious ray was literally shooting out of the negative metal plate, which is called the cathode, and flying across the vacuum to the positive plate, the anode.
And because it originated at the cathode, they just called them cathode rays. But at this point, they didn't actually know what a cathode ray was, right? Like, some scientists thought it was an invisible wave propagating through the ether, kind of like light or radio waves.
It was a massive debate. Was it a wave or was it a stream of physical material? So Thomson decided to settle the debate once and for all.
How did he do it?
Well, he knew that electrical fields and magnetic fields shouldn't affect a normal wave of light. Like if you hold a magnet up to a flashlight beam.
The beam doesn't bend.
Right, it doesn't bend.
Yeah.
So Thomson placed powerful electromagnets around his glass tube. And when he turned the magnets on, the glowing cathode ray violently bent away from the negative magnetic field and curved toward the positive one.
Okay, which immediately proves two things. First, because it can be manipulated by magnets, it isn't just an ethereal wave, it is a stream of physical, tangible stuff.
Yes.
And second, because it is repelled by a negative charge and attracted to a positive charge, the stuff itself must be negatively charged.
Thomson had definitively proved that the ray was made of negatively charged particles. He called them corpuscles, though we now know them as electrons.
Electrons?
But Thomson didn't stop there. He meticulously measured how much the magnetic field bent that stream of particles. And by doing the math on the angle of deflection, he was actually able to calculate the mass-to-charge ratio of these mysterious negative particles.
Okay.
And the number he got back was so absurd, he initially couldn't even believe it.
Wait, what did the math say?
The math revealed that these negatively charged particles were roughly 2,000 times lighter than a single atom of hydrogen.
You're kidding.
And hydrogen was the lightest known thing in the universe at the time.
Oh, wow. So he hasn't just found a new element. He has found a piece of matter that is a fraction of the size of an atom.
Exactly.
He has literally discovered a subatomic particle.
It was an earth-shattering paradigm shift.
Yeah.
Remember, Dalton said the atom was the absolute bottom of reality. It could not be cut.
The solid sphere.
Right. And Thomson just proved that not only can the atom be cut, but you can literally rip tiny negative pieces out of it using electricity.
Mm-hmm.
He discovered the electron, which eventually earned him the 1906 Nobel Prize in Physics.
Incredible.
But more importantly, he broke the atom.
Which is amazing, but it instantly creates a massive logical nightmare for physicists.
Oh, a huge headache.
Because let's think about this. If you touch a piece of wood or a glass of water, you don't get electrocuted. Matter in its natural state is electrically neutral. Its overall charge is zero.
Right.
But Thomson just proved that hidden inside these neutral atoms are thousands of negatively charged electrons.
Mm-hmm.
If you have a neutral overall score, but you know there are a bunch of minus ones hidden inside, simple math dictate there must be some plus ones hiding in there too, just to balance the equation out.
You've perfectly articulated the crisis Thomson faced. He knew there had to be a positive charge somewhere within the atom to neutralize his newly discovered electron.
But he couldn't see it.
No, he had no idea what that positive charge looked like or how it was structured. So he had to invent a completely new model of the atom to replace Dalton's solid sphere.
Okay.
He proposed that an atom is essentially a spherical, diffuse cloud of positive electrical charge. And embedded within this positive cloud, suspended like, insects in amber, were the tiny negatively charged electrons.
The source material notes this is famously called the plum pudding model, reflecting Thomson's British heritage.
Right, plum pudding.
But honestly, a plum pudding doesn't really resonate much today.
Not for most people, no.
Here's where it gets really interesting. Let's use a more modern, visceral analogy. Imagine a chocolate chip cookie before you bake it, like it's just a sphere of raw dough.
Okay, I like that.
The dough itself is a continuous, soft matrix of positive charge. And the chocolate chips scattered randomly throughout the dough are the negative electrons. Or, to use the source's alternative, think of a watermelon.
The watermelon is a great one.
Yeah. The red, soft, spread-out pulp is the positive charge, and the black seeds scattered through it are the electrons.
The watermelon is an excellent visualization because it really emphasizes that the positive charge is diffuse. It's spread out, not dense. Now, we look back at Thomson's model today and we know it's fundamentally incorrect.
Right.
But we really have to appreciate the sheer audacity and logic of it at the time. Thomson was overturning a century of established scientific dogma.
And this was around the time they were discovering radiation, right?
Yes, the discovery of radioactivity by Marie Curie and others was happening simultaneously, showing atoms literally ejecting smaller particles, which further proved the atom was a complex structure with moving parts, not a solid billiard ball.
It had internal anatomy.
Exactly. Thomson's model was the first genuine, intellectually rigorous attempt to map out the physical architecture of the subatomic world.
Okay, so to track our progress here, we started with Canada and Democritus imagining a philosophical, uncuttable dot. Thousands of years later, Dalton proves the dot exists as a solid, measurable sphere. That's right. Then Thomson fires up his vacuum tube, rips a negative electron out of the sphere, and replaces the solid ball with a watermelon of positive pulp and negative seeds. The atom has pieces.
It has pieces. But, science is a brutal arena. You don't just get to draw a picture of a watermelon on a chalkboard, declare victory, and go home.
Sadly not.
Every model must survive the crucible of experimental testing.
And the irony here is almost poetic, because the man who designs the experiment to test Thomson's watermelon model and ultimately completely annihilates it was a researcher who actually trained under Thomson himself.
It's a great plot twist.
It really is.
Yeah.
We move forward to the year 1911. We are at the University of Manchester, and we meet Ernest Rutherford.
A brilliant physicist from New Zealand.
Right, along with his assistants Hans Geiger and Ernest Marsden. And they design an experiment that is, without a doubt, one of the most elegant and shocking in the history of science. The gold foil experiment.
Rutherford's setup was just a masterclass in experimental design. It was conceptually simple, but mechanically incredibly difficult.
How so?
Well, he wanted to probe the internal structure of the atom. To do this, he needed a projectile, something microscopic he could basically fire at the atom to see what was inside.
A microscopic bullet.
Exactly. And he chose something called an alpha particle.
Okay, let's pause. We promised we wouldn't just throw terms around. What exactly is an alpha particle, and why did he choose it as his microscopic bullet?
Great question. So, an alpha particle is a type of radiation emitted by certain unstable elements, like radium or polonium, as they decay.
Okay.
In modern terms, an alpha particle is exactly the same as the nucleus of a helium atom. It contains 2 protons and 2 neutrons. But, for Rutherford's purposes, he only needed to know 3 things about it.
Which were?
It is incredibly tiny, it is very heavy compared to an electron, and it carries a strong positive charge. Furthermore, when emitted by radium, these alpha particles travel at roughly 1/10 the speed of light.
Whoa.
Yeah. So Rutherford essentially had a microscopic, positively charged, heavy artillery shell.
And his target for this artillery shell was gold foil. But why gold? Why not a sheet of iron or, I don't know, copper?
Because of gold's specific atomic properties. Gold is the most malleable metal on Earth.
Meaning you can flatten it.
Exactly. You can take a physical block of gold and hammer it so incredibly thin that it becomes translucent. Rutherford's assistants literally hammered gold foil until it was only about 1,000 atoms thick.
1,000 atoms? That's unimaginably thin.
He wanted the thinnest possible barrier, because if the foil was too thick, the alpha particles would just get absorbed and the experiment wouldn't work.
Yeah.
He wanted a barrier so thin he could observe exactly what happened as a particle passed through almost a single layer of atoms.
So the setup is this. You have a lead box containing radioactive radium emitting a narrow, highly focused beam of these heavy, fast, positive alpha particles.
Right.
You aim this microscopic machine gun directly at this impossibly thin sheet of gold foil. And surrounding the gold foil is a circular screen coated in zinc sulfide, which produces a tiny flash of light whenever an alpha particle hits it.
Exactly. And let me tell you, Geiger and Marsden literally had to sit in a pitch black room for hours.
Oh, man.
Yeah, letting their eyes adjust and then manually count these minuscule microscopic flashes of light on the screen to track where the alpha particles were going. It was grueling, tedious work.
I can't even imagine. Now let's look at this through the lens of 1911. Based entirely on J.J. Thomson's accepted watermelon model, what did Rutherford actually expect to happen when he turned the beam on?
Well, think about the physics of the watermelon. Thomson said the positive charge of the atom was like soft, spread-out pulp. It had no dense structure.
Right.
And the negative electrons were just tiny seeds. So if you fire a heavy, massive, ultra-fast alpha particle at a cloud of soft, diffuse, positive pulp, You expect the particle to behave like a cannonball being fired through a bank of fog.
It should just punch straight through.
It should punch straight through with zero resistance.
Maybe it bends a tiny microscopic fraction of a degree because the positive alpha particle is slightly repelled by the positive pulse.
Sure, slightly.
But essentially, 99.9% of them should just rip straight through the foil and hit the detector directly behind it.
That was the absolute mathematical expectation.
Yeah.
But that is not what Geiger and Marsden observed in that dark room.
No, it wasn't. They turned the beam on, and yes, the vast majority of the alpha particles act exactly as expected. They go straight through the gold foil as if it wasn't even there. But then they noticed something anomalous. Some of the particles are hitting the screen at wide, sharp angles. They're being deflected by 10, 20, 30 degrees.
Which is already highly suspicious. But then Rutherford asks them to look for something conceptually impossible.
What was that?
He tells them to check if any particles are hitting the screen in front of the gold foil. In other words, are any particles bouncing backward?
And they find them. A tiny fraction of the alpha particles, maybe like 1 in 20,000, hit the gold foil and ricochet straight back toward the radioactive source.
This is arguably the most famous moment of shock in scientific history. Rutherford was utterly flabbergasted.
I bet.
He later described the feeling with a quote that has become legendary in physics. He said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch naval shell at a piece of tissue paper and it came back and hit you."
I mean, let that analogy sink in for a second. You fire a massive explosive cannonball at a single sheet of Kleenex, and the cannonball bounces off the Kleenex and hits you in the face.
It completely breaks the laws of physics as they understood them.
Exactly. So wait, how on earth did Rutherford explain this impossible result?
Rutherford had to go back to his office, run the mathematical calculations on the angles of deflection, and completely throw Thomson's watermelon into the garbage.
Goodbye, plum pudding.
Yep. He realized there was only one physical reality that could produce this result. The positive charge of an atom cannot possibly be spread out like a soft cloud.
Because it bounced back.
Right. For a heavy, fast alpha particle to hit something and violently bounce backward, it must be colliding with an object that is incredibly dense, incredibly massive, and possesses a highly concentrated positive charge.
It hit a brick wall.
Exactly.
Yeah.
Rutherford deduced that almost the entirety of the atom's mass and all of its positive charge is not spread out, but packed into an unimaginably tiny, dense region right at the dead center of the atom.
Wow.
He named this central core the nucleus.
Okay, so the atom has this ultra-dense, rock-hard positive core. But wait, we have a contradiction here.
What's that?
If the atom has a rock-hard core, why did the vast majority of the alpha particles go straight through the foil without hitting anything at all?
This is where Rutherford's model gets truly mind-bending, and it fundamentally alters our perception of reality.
Okay, lay it on me.
If the core contains all the mass, but most projectiles pass through the atom without hitting anything at all, the mathematical conclusion that the nucleus is infinitesimally small compared to the total size of the atom, which means that almost the entirety of an atom is just completely, utterly empty space.
Okay, I need to stop you there because this is the part of atomic theory that always breaks my brain.
It does that to a lot of people.
Like, if I hit my hand against my wooden desk right now, it makes a sound, it feels entirely solid, my hand doesn't pass through the desk. But you are telling me that both my hand and the desk are mostly empty space.
It sounds like science fiction, but it is empirical reality. Let's scale it up. If you were to blow up the nucleus of a hydrogen atom to the size of a marble,
Okay, a marble.
and you place that marble right on the 50-yard line of a massive professional football stadium,
Got it.
the electron belonging to that atom would be a tiny gnat buzzing around the very highest seats in the bleachers.
No way.
Yes. Everything else between the marble and the gnat, the entire stadium, is nothing. It is a vacuum. It is empty space.
That is deeply unsettling. So why doesn't my hand pass through the desk?
Because of the electrons. Even though they are tiny, they are moving incredibly fast, creating a boundary of negative electrical charge around that vast empty space.
The gnats are moving fast.
Right. When the electrons in the atoms of your hand get close to the electrons in the atoms of the desk, those negative charges violently repel each other.
Oh, like pushing two negative magnets together.
Exactly. You aren't actually touching the physical mass of the desk. Your brain is interpreting the intense electromagnetic repulsion between two fields of empty space as solidity.
So touch is just a localized electromagnetic force field.
Pretty much.
That is wild. But let's bring it back to Rutherford. He figures out the tiny nucleus in the center and the vast empty stadium of space. But he has to miss a piece on the board. Where does he put the negative electrons?
Well, based on the physics of the time, he proposed the most logical solution. He suggested that the negative electrons must be orbiting the positive central nucleus.
Like planet.
Exactly, much like planets orbit the sun, held in place by electrical attraction rather than gravity. This became known as the planetary or solar system model of the atom.
I mean, it sounds beautiful, it's elegant, it mirrors the cosmos, it makes intuitive sense, but knowing the relentless cycle of this detective story, I feel like there's a trap door waiting to open.
There is a massive catastrophic flaw in the solar system model.
I knew it.
And it wasn't a flaw in chemistry, actually. It was a fatal conflict with the established laws of classical physics, specifically the laws of electromagnetism discovered by James Clerk Maxwell.
Okay, break the physics down for me. Why doesn't the planetary model work?
In classical physics, if you have an object moving in a circle, like an electron orbiting a nucleus, its velocity is constantly changing because its direction is constantly changing.
Right.
And a constant change in velocity means the object is in a state of continuous acceleration.
Okay, I follow that. Circular motion equals continuous acceleration.
Well, Maxwell's equations of electromagnetism dictated a strict rule. Whenever a charged particle, like an electron, accelerates, it emits electromagnetic radiation.
It gives off energy.
Exactly. It bleeds off energy in the form of light or heat. Therefore, if Rutherford's electron is orbiting the nucleus, it is accelerating, which means it must be constantly radiating energy.
And if it's losing energy, it can't maintain its orbit.
Exactly. Think of a satellite orbiting the Earth that suddenly fires its retrorockets and loses speed.
Its orbit decays. It falls.
Yes. If Rutherford's model was accurate according to classical physics, the electron would constantly bleed energy, its orbit would rapidly shrink, and it would spiral inward in a death spiral, crashing directly into the positive nucleus in a fraction of a microsecond.
And if the electrons crash into the nucleus, the structure of the atom collapses entirely.
Yes. If classical physics applied to Rutherford's model, every atom in the universe would have instantly collapsed in on itself the moment it was formed.
Which is bad.
Very bad. Matter as we know it, stars, planets, human beings, simply could not exist. The universe would be a soup of collapsed ultra-dense particles.
But I'm looking at my hand, and it hasn't collapsed into a singularity. The desk is still here. We exist.
We do.
So the experimental data from the gold foil absolutely proved the nucleus is there, but the established laws of physics mathematically proved that such a structure should destroy the universe. That is an incredible paradox.
It was a monumental crisis in physics. I mean, the finest minds of a generation were staring at a brick wall. The classical physics that had built the Industrial Revolution, the rules of Newton and Maxwell, they simply did not work inside the atom.
So we need new rules.
To save the atom and to save our understanding of reality, science required a conceptual leap so radical it bordered on heresy.
And to make that leap, we needed a revolutionary mind. Which brings us to 1913. And the arrival of a young Danish physicist named Niels Bohr.
Yes, Bohr.
Bohr looks at Rutherford's collapsing atom, he looks at the laws of classical physics, and he essentially says, if the rules say the atom shouldn't exist, then the rules are wrong. We need new rules for the microscopic world.
Bohr's insight was the dawn of quantum thinking applied to atomic structure. He postulated a model that boldly defied classical electromagnetism.
How did he fix the spiral?
Bohr declared that electrons don't just orbit the nucleus in any random path, and they don't gradually spiral inward. Instead, he proposed that electrons are locked into highly specific, fixed circular paths at exact distances from the nucleus.
Okay.
The source text refers to these as stationary states, orbits, or energy shells.
Let's try to unpack this because it is highly unintuitive.
It really is.
Like if I am running around a track, I can run in lane 1, or I can run in lane 2, or I can jog on the painted white line right between them. I can move anywhere I want. But Bohr is saying the electron doesn't have that freedom.
Right. Bohr argued that the atomic world is quantized. Imagine a ladder. You can stand firmly on the first rung. You can exert energy and climb up to the second rung. But you cannot stand in the empty air between rung 1 and rung 2. It is physically impossible.
You just fall.
Exactly. Bohr stated that electrons must exist entirely within these specific energy shells, which he labeled K, L, M, N, moving outward from the nucleus, or mathematically as N equals 1, 2, 3, 4.
Okay, so the electrons are locked into these specific ladder rungs. But how does that solve the death spiral problem? Why don't they still bleed energy and crash?
Because Bohr introduced a radical postulate. He simply declared that when an electron is occupying one of these allowed stationary shells, it does not radiate energy.
Wait, it just ignores Maxwell's rules.
It completely defies Maxwell's equations. It is a state of stable quantum equilibrium. It only absorbs or emits energy if it jumps from one allowed shell to another. But as long as it stays in its lane, its energy remains perfectly constant.
It's essentially a quantum leap.
Yes, literally.
Like, when an electron moves from shell 1 to shell 2, it doesn't travel through the space between them. It just disappears from shell 1 and instantly manifests in shell 2.
Exactly. It's like taking an elevator from the first floor to the second floor, but you never exist inside the elevator shaft.
That is so weird.
By establishing that energy is constant within these specific allowed shells, Bohr solved the stability crisis. Atoms don't collapse because the electrons are forbidden by the rules of quantum mechanics from occupying the space that would lead them into the nucleus. They are safe in their stationary lanes.
It is a stunningly bizarre solution, but it perfectly matched the experimental data of how atoms absorbed and emitted light.
It did.
So Bohr saves the universe from collapsing. We have a dense positive nucleus, and we have negative electrons locked in quantum shells. But to complete the modern architectural blueprint of the atom, we need to introduce one final character. Because we have the negative electron, we have the positive proton that makes up the nucleus. But the math still wasn't quite adding up, right?
Correct. Throughout the 1920s, physicists noticed a persistent discrepancy. If you took an atom of helium, which has 2 protons,
Okay, 2 protons.
you would expect it to weigh exactly twice as much as a hydrogen atom, which has 1 proton.
Right, simple math. 2 is double 1.
But it doesn't.
Okay.
Helium weighs 4 times as much as hydrogen.
4 times.
There was mysterious, unaccounted-for mass inside the nucleus.
So if it's not protons and it's not electrons, what is it?
Well, it wasn't until 1932, which is astonishingly recent, considering this entire journey we've been on, that an English physicist named James Chadwick cracked the final puzzle.
1932.
Yes. He conducted experiments bombarding beryllium with alpha particles and discovered a completely new subatomic particle residing inside the nucleus alongside the protons.
And he called
He
it.
called it the neutron.
Why did it take until 1932 to find it? I mean, Thomson found the electron in 1897. Why did the neutron manage to hide for 35 years?
Because the neutron is exactly what its name implies, electrically neutral.
Oh, it has no charge.
It has 0 electrical charge. Electrons and protons are relatively easy to detect because their charges react violently to magnetic and electric fields. They leave tracks you can see.
Right, they bend.
A neutron, however, is an electromagnetic ghost. It just sits in the nucleus, adding massive amounts of weight to the atom, but it remains electrically silent. Chadwick had to use indirect collision methods, basically playing subatomic billiards to prove it was there by measuring how it knocked other particles around.
So let's recap our fully realized, completed classical blueprint of the atom.
Let's do it.
If we were to shrink down to a billionth of a meter, we would see an unimaginably dense, microscopically tiny core, the nucleus made up of positive protons and neutral neutrons bound tightly together.
Right.
Surrounding that nucleus is a vast, mind-boggling expanse of pure empty space. And zipping around in that empty void, locked into very specific, mathematically rigid quantum energy shells, are the tiny, negatively charged electrons.
That is the beautiful, terrifying, stable architecture that constructs our reality.
It is a masterpiece of scientific discovery. But here's the thing that really trips me up.
What's that?
If every single atom in the universe is constructed out of those exact same 3 ingredients, protons, neutrons, and electrons, how do we get the infinite complexity of the material world?
Ah.
I mean, what is the actual mechanical difference between the carbon atom that makes up the DNA in my cells, the oxygen atom I am breathing into my lungs, and the iron atom in the steel girders of a skyscraper? They are all just piles of the exact same 3 particles.
That is the perfect question to launch us into the final phase of our deep dive, decoding the modern elemental toolkit.
Okay, great.
Because you are right. Matter isn't about what ingredients you have, because everyone has the same 3 ingredients. The entire diversity of the universe is dictated purely by the number of those ingredients and how they are arranged.
Just the numbers.
Yes. And to understand how we categorize that, we need to decode some specific terminology from the source text.
Let's do it. We will avoid sounding like a textbook glossary, but we really need the keys to the kingdom here.
We do.
Let's start with the most fundamental concept. The atomic number. What is it, and why does it matter?
The atomic number is the absolute soul of an element. It is defined simply as the exact number of protons located inside the nucleus of an atom.
Just the protons.
That's it, just a head count of protons.
Right.
But that single number entirely dictates the identity of the atom. If an atom has precisely 6 protons in its nucleus, it is carbon. It will always behave like carbon.
Okay.
If you were to somehow force a 7th proton into that nucleus, it instantly ceases to be carbon. It transforms into nitrogen. If it has 79 protons, it is gold.
Wait, so alchemy is technically real? Like, if I have a block of lead which has 82 protons, and I can somehow systematically strip away exactly 3 protons from every atom, I will literally be left with a block of gold which has 79 protons.
Theoretically and experimentally, yes.
You're kidding.
No, we can actually do that inside modern nuclear reactors or particle accelerators.
Oh.
Now, it costs millions of dollars to produce a microscopic fraction of a cent's worth of gold, so it's not economically viable. But the physics is absolutely sound. The proton count is the unchangeable identity tag of the element.
Okay, so protons equal identity. What about the mass number?
The mass number is simply the total head count of the heavy weights in the atom. It is the number of protons plus the number of neutrons in the nucleus.
And we ignore the electrons.
We completely ignore the electrons when calculating mass because they are so astonishingly light. Remember, they're about 2,000 times lighter than a proton.
Oh, right.
Adding an electron to an atom's weight is like tossing a grain of sand onto a battleship. It doesn't change the scale. So mass number is just protons plus neutrons.
So if a standard carbon atom has 6 protons and 6 neutrons, its mass number is 12. Simple arithmetic.
Very simple.
But this brings us to a slightly more nuanced term from the source: isotope. I hear this word all the time in sci-fi movies and documentaries about nuclear energy, but what is an isotope mechanically?
To understand isotopes, think of them as siblings in a chemical family. Isotopes are atoms of the exact same element, meaning they have the exact same number of protons, the same atomic number, but they have a different number of neutrons.
Ah, so they have the same identity, but they weigh a little more or a little less.
Precisely. Let's stick with our carbon example. The vast, overwhelming majority of carbon in your body and in the universe is carbon-12. 6 protons, 6 neutrons. It is stable and happy.
Okay.
But high up in the Earth's atmosphere, cosmic rays from deep space continuously bombard nitrogen atoms, occasionally knocking a neutron into a carbon atom.
Interesting.
This creates an atom with 6 protons, so it's still carbon, but it now has 8 neutrons. Its mass number is 14. This is carbon-14.
Okay, so carbon-14 is an isotope of carbon. It behaves chemically identical to normal carbon, but it's heavier.
Yes, and crucially, it is unstable. That extra weight makes the nucleus jittery, and eventually it decays, releasing radiation.
Oh, is this how carbon dating works?
It is the entire basis of carbon dating. Plants absorb carbon-14 from the atmosphere during photosynthesis. Animals eat the plants. When the plant or animal dies, it stops absorbing new carbon-14, and the heavy isotopes slowly decay at a mathematically predictable rate.
So it's a clock.
Exactly. By measuring how much carbon-14 is left in a fossil, we can calculate exactly when it died. Isotopes aren't just abstract concepts. They are the clocks we use to measure the history of life on Earth.
That perfectly grounds it. Isotopes are variations in weight for the same element. Now, the source text also mentions isobars. What is the distinction there?
Isobars are essentially the inverse of isotopes. Isobars are atoms of completely different elements, meaning they have different atomic numbers, different amounts of protons.
Okay.
But by sheer mathematical coincidence, their total combination of protons and neutrons happens to add up to the exact same mass number.
Give me a real-world example of this coincidence.
The source material actually highlights a perfect one. Imagine you have an atom of argon. Argon has 18 protons. A specific isotope of argon also has 22 neutrons.
So 18 plus 22.
Gives it a mass number of 40. Now look across the periodic table at an atom of calcium. Calcium has 20 protons. A standard calcium atom has 20 neutrons.
And 20 plus 20 also equals 40.
Exactly, a mass number of 40.
So argon is a noble gas that doesn't react with anything, and calcium is a reactive metal that builds our bones. Completely different identities, completely different chemical behaviors, but if you put them on a microscopic scale, they weigh the exact same amount. They are isobars.
Exactly. It highlights how the nucleus dictates weight and identity, but it doesn't dictate how the atom interacts with the world. To understand how atoms actually build the universe, we have to look away from the nucleus and look at the electrons.
Which brings us to the final, and I would argue the most profoundly important concept in this entire toolkit: valency. If the protons are the soul of the atom, valency is its personality.
I love that analogy. Valency is formally defined as the combining capacity of an atom. It dictates how an atom will bond with other atoms. And valency is governed entirely by the electrons residing in the very outermost energy shell of the atom, the highest rung on Bohr's ladder.
Let's translate this into human behavior because it makes the chemistry so much easier to grasp.
Good idea.
It all boils down to a concept called the octet rule. Atoms, fundamentally, are driven by an almost mathematical desire for profound, stable equilibrium. They want to rest. And for an atom, chemical rest means having exactly 8 electrons in its outermost shell.
Or just 2 if it's a tiny atom like hydrogen or helium.
Right. But generally, 8 is the magic number of stability.
And what's fascinating here is that this relentless quest to acquire exactly 8 outer electrons is the engine that drives absolutely every chemical reaction in the universe. An atom's valency tells us how far away it is from that goal of 8, and therefore how desperately it will behave to get there.
Right. If an atom, let's say sodium, has a full inner shell, but only one solitary, lonely electron buzzing around in its outermost shell, it feels unbalanced.
Very unbalanced.
It doesn't want to try and steal 7 electrons from someone else to get to 8. That's way too hard. It's much easier to just violently eject that one outer electron, just give it away, so that the full, stable shell underneath becomes its new outer layer.
Exactly. Sodium is highly reactive because it desperately wants to get rid of that one electron. Now, on the other side of the periodic table, you have an element like chlorine.
Okay, chlorine.
Chlorine has 7 electrons in its outer shell. It is agonizingly close to the perfect 8. It is incredibly anxious. It will aggressively rip an electron away from any atom it encounters to complete its set.
So if you put a piece of sodium, which is desperately trying to throw away an electron, next to a cloud of chlorine gas, which is violently trying to steal an electron,
You get a highly exothermic, explosive chemical reaction. The sodium donates its electron to the chlorine. Suddenly, both atoms have perfectly stable, full outer shells. They find peace. But in doing so, the sodium becomes positively charged because it lost a negative electron, and the chlorine becomes negatively charged because it gained one. These opposite charges lock them together in an unbreakable electromagnetic embrace. They bond.
and a highly reactive metal and a toxic green gas bond together to form sodium chloride. Table salt.
Yep.
The stuff we put on our French fries.
Yes. It is this exact mechanism, the sharing, stealing, and giving away of outermost electrons to fulfill the octet rule that causes atoms to stick together.
That's incredible.
It dictates how 2 hydrogen atoms share their electrons with 1 oxygen atom to create water. It dictates how carbon atoms form long chains to build the proteins in your muscles and the DNA in your cells. Every physical structure, every biological process, every medication, every plastic, every breath you take is just a manifestation of tiny, invisible atoms negotiating with each other to get stable outer shells.
It is genuinely staggering to realize that the entire chaotic, beautiful complexity of biology, chemistry, and engineering ultimately boils down to subatomic particles trying to solve a simple math problem of reaching the number 8.
It is the grand unifying rule of the molecular world. Protons tell you what the element is, neutrons determine how heavy its variations are, and the outermost electrons, the valence electrons, dictate how it socializes, bonds, and interacts with the rest of the universe.
That is just brilliant. We have covered an immense expanse of scientific history and theory today. Let's do a quick recap to anchor everything we've explored.
Sounds good.
We started over 2,000 years ago with Canada in India and Democritus in Greece, sitting in nature, using pure logic to deduce that matter must eventually hit an uncuttable limit, the Parmanu or atomos. We leaped forward to 1808, where John Dalton grounded that philosophy in experimental data, proving that chemical reactions rely on solid, unbreakable atomic spheres. Then, in 1897, J.J. Thomson ripped an electron out of that sphere with a cathode ray, giving us the watermelon model of negative seeds and positive pulp.
The plum pudding.
Right. Rutherford then shot literal atomic cannonballs through the watermelon, proving that the atom is overwhelmingly empty space centered around a microscopic, rock-hard nucleus. And when the laws of classical physics threatened to collapse Rutherford's atom, Niels Bohr stepped in and locked the electrons onto stable, quantized energy tracks.
The latter.
The latter. Finally, Chadwick found the ghost-like neutron, completing the blueprint, and we learned how protons, neutrons, and the pursuit of 8 valence electrons build every physical thing we know.
It is a remarkable, humbling progression. And I think the most important takeaway is how it highlights the true nature of science. Science is never just one solitary genius having a eureka moment in a vacuum.
Never.
It is a relentless, multi-generational baton pass. It is each generation having the courage to find the fatal flaws in the previous generation's prize model, tearing it down, and building something more precise, more weird, and closer to reality.
So, to our listener, the next time you touch a wooden table, or drink a glass of water, or simply take a deep breath of air, pause and take a moment to really conceptualize what you are actually interacting with. You aren't touching solid matter. You are interacting with billions upon billions of tiny, stable, invisible quantum systems.
Yep.
They are sharing their outer electrons, maintaining their stationary energy states, and quite literally holding the electromagnetic fabric of your reality together.
It's a profound perspective shift. And, I want to leave you with one final, slightly provocative thought to mull over.
Oh,
If you look at the very end of the source text's timeline, it hints that our modern understanding is based on a quantum mechanical model, and it explicitly states that the true nature of the atom is still being discovered.
wait, you mean Bohr's perfect quantum ladder isn't the end of the story?
Not even close. The Bohr model is brilliant for education, but modern physics has already moved way past it. We now know electrons don't really orbit in neat little planetary tracks.
We don't.
No, they exist in bizarre clouds of probability. They behave as both particles and waves simultaneously. We've smashed the protons and neutrons open and found even smaller, stranger things inside them called quarks, held together by gluons.
Oh my God.
And we are currently theorizing that those quarks might just be vibrating strings of multidimensional energy.
So the journey is still going.
Absolutely. Think about it. Human understanding evolved from pure philosophical musings to Dalton's billiard balls to Thomson's puddings to Bohr's quantum shells in just a little over a century. So what is the atom going to look like to a student learning about it 100 years from now?
That's a great question.
Are we finally at the bedrock of reality, or are quarks and probability clouds just the next watermelon waiting to be shattered by a new experiment?
Yeah.
Are we just barely scratching the surface of an architecture that is infinitely deeper and fundamentally more bizarre than we can currently imagine?
That is a staggering thought to end on. We've come so far, but the diagnostic X-ray of the universe might still just be a blurry snapshot. There is always more to discover. Keep looking closely at the world around you because nothing is as simple as it seems. Until next time.